expert lectures and seminars, and he's completed 10 research projects funded by national and international agencies and has published 151 papers and wrote 7 books. So it's an honor to have you, sir, for chairing this technical session. Sir.
Okay. Good morning, one and all. On behalf of the organizing committee, we welcome one and all for this academics sessions of today's conference. During this first academic session, there are 2 invited talks, one by Dr. Aparna Lakshmanan and another by Professor Samir Vaidya. And it is my duty to remind the participants that there is a little bit change in the duration of the academic session planned today. In contrast to the scheduled timing, this academic session, first talk shall be of 45 minutes instead of 1 hour 15 minutes notified. It is from 10:30 to 11:15, and the second talk shall be from 11:15 to 12. Now let me invite Dr. Aparna Lakshmanan from CUSAT, Cochin University of Science and Technology. I am known to her and vice versa for quite some decades. She has completed her master's degree from Cochin University of Science and Technology with the first rank in MSc, and subsequently she has completed her PhD through the same department after availing NET fellowship under the guidance of Professor Ambat Vijay Kumar, who was the keynote speaker yesterday. And she started her teaching in a college affiliated to MG University, situated at Aluva, St. Xavier's College, and she served there for 16 years. And recently, during October 2021, she moved to her parent department, namely Department of Mathematics, Cochin University of Science and Technology, and she has been continuing there. Of course, she has won several awards in spite of the time schedules. Just let me say, she has won Kerala Young Scientist Award and others. And she has been concentrating on problems related to transformation of graphs and domination and other topics of graph theory. And she has got a membership in academic bodies like American Mathematical Society, Indian Mathematical Society, Ramanujan Mathematical Society, Academy of Discrete Math and Applications, and Kerala Mathematical Association. In this component, she has served as secretary for Atmiya for 4 years during 2016 to 20. And she has got to her credit about 30 papers in reputed international journals. She has got some good academic collaboration with people like Sandy Klasser, and she has visited that country also. And it is my happy occasion that I invite Dr. Aparna Lakshmanan to deliver a talk on gamma graphs of a graph. Please.
Good morning to all of you. First of all, let me thank Professor Tamil Selvam sir for that wonderful introduction, and Professor Chirag for inviting me to deliver an invited talk in this national conference. So let me share my screen. So today I'll be talking about gamma graph of a graph. Actually, gamma graph is a kind of a graph operator, the details into which we will look into. Just to begin with, I need the definition of domination. I assume that almost all of you will be knowing the definition of domination, but still, for the sake of completeness, I have just included the definition. When you are given a graph, a subset S of the vertex set V is called a dominating set if every vertex is either present in that set or is adjacent to a vertex in that set. So if you take the entire vertex set, definitely that will be a dominating set. But we are not interested in that. We try to minimize the cardinality of the dominating set. A dominating set is said to be minimal if no proper subset of that dominating set is a dominating set, and the domination number is the minimum cardinality of a dominating set. This we denote by gamma of G. And a gamma set is a dominating set with cardinality gamma of G. Just recall that these gamma sets need not be unique. You give me a graph, there are graphs which have only one gamma set, and there are graphs which have plenty of gamma sets in it. Before moving to the definition of gamma graphs, there are some variations for this domination number. In usual domination number, our condition was that every vertex is either present in the set or is adjacent to a vertex in that set. If we want a bit more, we can restrict ourselves to the case that every vertex must be adjacent to some vertex in S. It is not enough that that vertex is present in S, but must be adjacent to some vertex in S. If that is the case, we call such sets as total dominating sets, and the minimum possible cardinality is the total domination number. And again, when we move on to the application side of domination, sometimes we may require that. Yes. Yes. Shall I proceed? I hope.
You proceed.
Okay. So sometimes we may require that there exists a specific type of relation between the vertices in the dominating set. If from the dominating set we can find a perfect matching, then such sets are called paired dominating sets, and the domination number is called paired domination number. And if there is no relation at all between the vertices in the dominating set, we call such dominating sets as independent dominating sets. And if they are totally connected, that is from any vertex, I can move to any other vertex in S without moving out of S, we say that such dominating sets are connected dominating sets. And we call the domination parameter as connected domination number. So, in fact, hundreds and hundreds of variations of domination number are now available in the literature. There is a textbook, Fundamentals of Domination in Graphs. The second edition is now also the advanced topics in domination graphs is also available due to Haynes, Atmiya, and Slater. That gives you a very good collection of variations of domination numbers. In fact, I think that many variations of domination numbers were introduced due to a problem suggested in a 1919 paper by Basco and Tuza. The paper is Dominating Cliques in P5 free graphs, published in Periodica Mathematica Hungarica. In that, they have posed a question. Let P be a property of the vertex set in graphs. Characterize all graphs having a dominating set which satisfies the property P. So when we come to paired domination number, the condition is that we need a perfect matching in that set. When we come to independent domination number, the condition is that the set must be independent. The set S must be independent. Like that, we have plenty of properties related to graphs. You can choose one property. Make sure that your dominating set satisfies. I think someone unmuted by mistake. Okay, let me continue.
That is
okay. So if your dominating set satisfies that property P, then it is well and good. Okay. So based on this paper, based on this problem suggested in that paper, many variations of domination numbers were introduced and studied. Many of them have very good application, and I'm sorry to say that many are useless apart from the basic academic interest. Okay. So moving on to another area in graph theory, graph parameters and graph operators. I have clubbed these two because both are functions. Graph parameters and graph operators are functions defined on the same domain, defined on the class of all graphs. If you need, you can restrict yourself to any subclass also, but in general, it is defined for the class of all graphs. So the domain is fixed. If the range is a collection of numbers, we call such functions as graph parameters. And if the range or codomain is again a collection of graphs, we call such functions as graph operators. So graph parameters are functions defined from graphs to numbers, whereas graph operators are functions defined from the class of all graphs to itself. Again, we can restrict the domain and codomain according to our necessity. But the basic thing is this. The gamma graphs which we are discussing today are basically graph operators. That is, you give me a graph G, I can produce a graph gamma dot G. So gamma is my function. When I apply that function to the graph G, I obtain a new graph and I call that graph as gamma graph. So how do we obtain this new graph? The vertex set of gamma dot G is basically the gamma sets of G. That is why I just recalled the definition of domination number and gamma sets in the beginning. So our vertex set is precisely the gamma sets of the graph G. And two vertices are made adjacent to each other if the corresponding gamma sets differ exactly at one vertex. If so, we make them adjacent. Please note that this is different from the angle of intersection graphs. In the case of intersection graphs, we have vertex sets as of G minus 1 vertices. These two sets differ exactly at one vertex. Then we make them adjacent to each other. Here you have an example. Our dear Peterson graph is here. First, we need to know the domination number of Peterson graph. It is well known the domination number is 3. And coming to dominating sets, say if I choose 1 and 3, then the outer cycle is entirely dominated. And 6 and 8 are also dominated. Now I need to dominate 10, 7, and 9. If I need to do it with one vertex, the only possibility is to take 7. So once you fix 1 and 3, the third vertex must be 7. This is important for us. That is why I am stressing on that point. Once you fix two vertices, 1 and 3, the third vertex must be 7. If you go on like that, you get 10 dominating sets, and you can see that once you fix two vertices, the system automatically fixes the third vertex. What does that indicate? Two dominating sets cannot differ exactly at one position, because once you fix two vertices, the third vertex is automatically fixed. Okay. So what will be the gamma graph of Peterson graph? Due to this particular property, the gamma graph of Peterson graph will be trivial graph. That is a totally disconnected graph with 10 vertices, since there are 10 different gamma sets, that is dominating sets of cardinality 3. So Peterson graph is a well-connected graph, and you can see that the gamma graph is totally disconnected. So from that we get an information that is, even if the graph G is connected, the gamma graph need not be connected, and even the worst case can happen. It can be totally disconnected. The reverse case is also there. Even if the graph is not connected, it is possible that the gamma graph is totally connected. Say gamma graph even can be complete. That is also possible. You take two K2s, two independent edges, look for all dominating sets, and you can see that the resultant gamma graph will be K4, the complete graph. Okay, so regarding connectivity, there is no relation between a graph and its gamma graph. Examples of gamma graphs, all complete graphs are gamma graphs, because you start with a complete graph, the domination number is 1. Any vertex is a dominating set. So there is only one vertex in the dominating set. So between two dominating sets, the difference will be only for one vertex, since it contains only one vertex, right? So every vertex is a dominating set, and in gamma graph, all these vertices are adjacent to each other. So the complete graph of, the gamma graph of complete graph is that graph itself. So every complete graphs are gamma graphs. Again, it has been proved that all trees are gamma graphs, all unicyclic graphs are gamma graphs. In fact, the concept was introduced by Professor N. Sridharan and one of his students, K. Subramanian. They published the first paper on gamma graph of a graph in the Bulletin of Kerala Mathematical Association in the year 2008. Followed by that, the next publication was again from the same team in JCMCC in 2009, and the third paper was from in fact, from our side. But before that, not before that, just after that, another paper got published with the name A Note on Gamma Graphs. This got published in AKC International Journal of Graphs and Combinatorics. The notation is the same, gamma graph. The notation is the same, but their definition is different. Just after the paper got accepted for publication and the processing was going on, they noticed that there already exists a graph with the same name with just 3 papers published in that direction. And you can see that they added one note towards the end, telling that there are 3 such papers, 2 from Professor Sridharan and his student, and 1 from myself and my guide, Professor Ambad Vijay Kumar, with the name gamma graph and same notation, but the concept is different. So if you are proceeding to work in gamma graphs, beware, there are 2 different gamma graphs. You have to be sure which gamma graph you are choosing when you are reading the papers. Okay. So I just wanted to point out that with the same name, there is another person, don't get confused. And a 4th paper on gamma graphs was published again by Professor Sridharan and Amuta, co-authored with Professor S.B. Rao, which says induced subgraphs of gamma graphs, published in Discrete Mathematics, Algorithms and Applications in 2013. In that paper, they have proved that every induced subgraph of a gamma graph is a gamma graph. This is a bit important. This result we will be using in a later contest. And in that paper, they have also proved that if H equal to gamma dot G, then there exists a sequence Gn of non-isomorphic graphs such that H is equal to gamma dot Gn. What is the relevance? This deals with the inverse problem. So given a graph G, you can find the gamma graph of that. Gamma dot G, you can find. So given a graph H, what about the reverse case? Given a graph H, does there exist a graph G for which H is equal to gamma dot G? That is a question. And if it exists, is that unique? That is again another question. The answer to the first question is no, there are graphs. We will come to that. And the answer to the second question was negatively answered in this 2013 paper. It need not be unique. Once H is a gamma graph of some graph G, we can find infinitely many graphs. They have obtained a sequence of graphs, G1, G2, etc. such that for all those graphs, the gamma graph is H. So the inverse case is not unique. Once H is a gamma graph, there exist infinitely many graphs for which H is a gamma graph. But still, there are graphs H which are not gamma graphs. So to proceed further, I need the definition of Cartesian product of graphs. Most of you will be knowing, but still, yes, just for the sake of completion. If G equal to V1 E1 and H equal to V2 E2, then the Cartesian product of G and H is the graph with vertex set ordered pairs V1 V2, where V1 is from the vertex set of G and V2 is from the vertex set of H. And 2 vertices, V1, V2 and V1 dash, V2 dash are made adjacent in the Cartesian product if either V1 equal to V1 dash either V1 equal to V1 dash and V2 is adjacent to V2 dash, or V1 is adjacent to V1 dash and V2 equal to V2 dash. If one condition is satisfied, then there is adjacency. Okay. So here is an example for Cartesian product of two graphs. You can see that there will be H number of G's and G number of H, where G and H denotes the cardinality of vertex set of G and H. Here again, there is another example of Cartesian product of two graphs. Coming to forbidden subgraphs, this is the point where I need that result which I earlier mentioned. If G is a gamma graph, then every induced subgraph of G is also a gamma graph. This is already proved in that 2013 paper published in DMA, which indicates that gamma graphs can be characterized using forbidden subgraphs. So what is a forbidden subgraph? A graph H is forbidden for a property P if G satisfies property P, then G cannot have H as an induced subgraph. If that is the case, we say that H is a forbidden subgraph for the property P. If no proper subgraph of H is forbidden, then we say that H is a minimal forbidden subgraph. Some classes of graphs can be characterized using forbidden subgraph characterization. That is, if you find H as an induced subgraph, you can be sure that the graph G does not belong to a particular class of graphs. If such a characterization exists, we say that need not be that with one single graph, it can be with a collection of graphs also. If such a characterization exists, we say that that graph class can be characterized using forbidden subgraphs. And if a graph class satisfies vertex hereditary property, then such class can be characterized using forbidden subgraphs. Here in 2013, it has been already proved that gamma graphs do have vertex hereditary property. That is, if G is a gamma graph, then every induced subgraph of G is also a gamma graph. So we can characterize gamma graphs using forbidden subgraphs. It is true that we can, but the characterization is still open. So that comes under the list of open problems. Okay. So we were looking for forbidden subgraphs of gamma graphs. In fact, in the first paper due to Professor N. Sridharan, a graph was given. That is, three triangles sharing a common edge. That graph was given and a note was added that this particular graph is forbidden for the class of all gamma graphs. So we were interested in that part and we tried to find all forbidden subgraphs of gamma graphs on 5 vertices. For that, we had some other observations, which includes the Cartesian product of two graphs. That is why I have just introduced the definition of Cartesian product also. One of our observations is that if H1 is gamma dot G1 and H2 is gamma dot G2, that is H1 and H2 are gamma graphs of G1 and G2, then the gamma graph of G1 union G2 union K2 is the Cartesian product of H1, H2, and then again a Cartesian product with K2. Okay. So what does that indicates? If H1 and H2 are gamma graphs, if H1 and H2 are not forbidden for the property of being a gamma graph, then H1 Cartesian product H2 is not a forbidden subgraph for gamma graphs. So once if we know that H1 and H2 are not forbidden, we need not worry about H1 Cartesian product H2. That is again not going to be a forbidden subgraph. Okay. Again, another observation was that every minimal forbidden subgraph will be connected. That is, if you know that G1 union G2 is forbidden for the class of all gamma graphs, then either G1 or G2 must be forbidden, which means G1 union G2 is not minimal. So when we are looking for minimal forbidden subgraphs, we can restrict ourselves to connected graphs. And we could completely settle the problem of finding forbidden subgraphs on 5 vertices. There are precisely 4 graphs on 5 vertices, which are forbidden for the class of all gamma graphs, namely K32, K2 join 3K1, K2 join P3, and K2 union K1 join 2K1. I'll just quickly give you an idea of proof of K32 being forbidden. This is simple. If possible, assume that K32 is present as an induced subgraph of a gamma graph. So corresponding to this K32, I need vertices. I need gamma sets, right? Gamma sets are my vertices. So let those gamma sets be U1, U2, U3 and V1, V2, which gives the parted set of K23. Okay. So every Uy is adjacent to Vj and Uys are not adjacent to each other. Vjs are not adjacent to each other. Let U1 be U1, U2, etc. Uk, where K is the domination number of K32. Not K32, domination number of G, for which K32 is the gamma graph. Okay, so U1 is this. U1 must be adjacent to V1. So U1 and V1 can differ at most one position. Without loss of generality, I assume that U1 is absent and instead of that, a new vertex V1 is present there. So vertex at V1 will be V1, U2, etc. UK. V2 is also adjacent to U1 and V2 should not be adjacent to V1, which forces V2 to be of the form U1 etc. UK in which U2 is absent and some other V2 is present. Okay, again without loss of generality, we can assume like that. Now coming to U2, U2 must be adjacent to both V1 and V2. So it can differ at most at one position from V1 and V2, and U2 should not be adjacent with U1, which forces us to choose U2 as V1, V2 together with U3, etc. UK, so that it will be adjacent to V1 and V2, but not to U1. But now there is no way in which you can choose not V3, but U3. Okay, we cannot find a U3 such that it is adjacent to both V1 and V2, adjacent to both V1 and V2 and non-adjacent to U1 forces us to choose that gamma set as V1, V2, etc. UK, and that we have already named as U2. So there is no choice left for the set, for the gamma set U3. Hence K32 is a forbidden subgraph. In similar track, but not that easy, we can just characterize all forbidden subgraphs on 5 vertices. Now moving on to 6 vertices. Again, there are 4 vertices on 4 graphs on 6 vertices, which are forbidden subgraphs for gamma graphs. In fact, this part I have given to one of my UG, to 2 of my UG students to do as a UG project. Of course, apart from their usual curriculum, I just told them this is interesting and this is solvable for you. So they tried and they found these 4 graphs. But maybe at the same time, someone else was also trying the problem, and a paper got published in 2017. Before we could communicate our paper, got published in 2017, which again proves that these 4 are the forbidden subgraphs. But our proof techniques are totally different. The idea of proof given by my students was that a crude idea, in fact. On 6 vertices, there are 156 graphs. We already know that forbidden subgraphs will be connected. So we need not look into all this 156 graphs. There are only 112 connected graphs, non-isomorphic obviously, on 6 vertices. So we need to check only 112 graphs. From that, we know that complete graph is already a gamma graph. So we can eliminate that. So there are 111 graphs left. Again, we know that trees and unicyclic graphs are already proved to be gamma graphs. So we can eliminate those graphs. We'll be left with 92 graphs. It's like zeroing. Okay, so we are left with 92 graphs. And on 5 vertices, we have 4 forbidden subgraphs of gamma graphs. If any of those 4 graphs are present as an induced subgraph, then that graph on 6 vertex is not a minimal forbidden subgraph because it already contains a subgraph which is already forbidden. So we can eliminate those. So we'll be left with 52 graphs. And on 6 vertices, there are 2 Cartesian products, connected Cartesian products, namely P3 box K2 and K3 box K2. Cartesian products are not forbidden since the base graphs are not forbidden. So we are left with 50 graphs. And for 46 graphs, they obtained realizations. They took all those 46 graphs, and in fact took 50 graphs, and 46 graphs admitted realizations, and 4 graphs, we can prove that these graphs cannot be gamma graphs using arguments similar to the way in which we proved K32. Okay, but this idea we cannot extend further because as n increases, the number of graphs exponentially increases, and it is not easy to just do the zeroing and identify all forbidden subgraphs. So we need to develop a better technique to identify forbidden subgraphs. So these are the forbidden subgraphs on 6 vertices. Okay, 4 forbidden subgraphs on 5 vertices and 4 on 6 vertices. But there can be more which are yet to be identified and which will be of cardinality n greater than order greater than or equal to 7. Okay. Now we were just looking towards the closure property under graph products. We could see that closure property is not satisfied for tensor products and strong products because from very small cases itself, the closure property is lost. Say K5 tensor product K2 is K55 and K32 is an induced subgraph of K55 and K32 is forbidden for gamma graphs. Okay, so tensor product do not satisfy closure property. Coming to strong products, K3 is a gamma graph, P2 is also a gamma graph. When you take strong product, it is not equal to P3 join K2, but it contains P3 join K2 as an induced subgraph, and P3 join K2 is forbidden for gamma graphs. So strong products are also not closed for the class of gamma graphs, but Cartesian products are closed. As we have already observed, Cartesian product is closed under the operation of gamma graphs. Coming to another class of graphs called co-graphs, complement reducible graphs. These are graphs which can be reduced to isolated vertices by repeatedly taking complements within components. Okay, C4, you take complement, you get 2K2. Again, you take complement within components, you get 4K1. From the definition of co-graphs, we can see that self-complementary graphs won't be co-graphs. Again, graphs for which the complement is connected won't be a co-graph because when we take complement, we get back G because there is only one component, right? So if G is a co-graph, then its complement must be disconnected like that. And there are many interesting properties of co-graphs. I'm not going into the details of it. I just wrongly got the idea that I have got 1 hour, 15 minutes. Now it is only 45 minutes, so I have to rush. Okay, so there are many interesting properties for co-graphs. And for co-graphs, we have found the gamma graph of a co-graph based on a particular partition for the vertex set. So it will look like a Cartesian product of KPI box KQI. Each partition will look like that. And the proof is by induction on the number of vertices. Again, for co-graphs, the diameter is less than or equal to 2, but it is not true that every graph for which diameter less than or equal to 2 is a co-graph. But this property is maintained for gamma. It's not maintained for gamma dot G. When we move to disconnected co-graphs. If the co-graph is connected, then the property is maintained. Whereas if we move on to disconnected co-graphs, say if you take C4 union K2, the diameter of the gamma graph will be 3. So if the base graph is disconnected, the property is lost. But if we are restricting ourselves to connected co-graphs, then only the question of diameter comes, right? So in that case, the diameter of gamma dot G is less than or equal to 2. Here is a list of gamma graphs of various graph classes. For complete graphs, it is Kn itself. In fact, if you take a graph in which there are n universal vertices, then the gamma graph will be Kn, because if there exists a universal vertex, the domination number is 1, and every universal vertex gives you a dominating set, and in the gamma graph, they will be adjacent to each other. Again, the gamma graphs of paths and cycles are computed. We get three different cases based on where the number of vertices is a multiple of 3 or 3 plus 1 or multiple of 3 plus 2. And for complete bipartite graphs KMN, it is Cartesian product of Km box Kn, provided both M and N are greater than 2. If one of them is equal to 2, then it becomes Kn box K2 join K1, because the two vertices in one partite set also forms a dominating set. Otherwise, for KMN, the thing is that you have to take one vertex from one partite set and other vertex from the second partite set. Okay. Now, another direction in which we can think is what is the impact of gamma graphs on various graph parameters. Say what happens to click number. Say for KMN, the click size is 2. You know that. Okay, click is the maximum order of a complete graph. And when you take the gamma graph, you can see that it is Km box Kn, right? So the click number is n there. Even when the click number of starting graph is 2, we can obtain graphs for which it is as large as n, where n is arbitrary. So how gamma graphs influences various graph parameters? That is an interesting question. The case of click number, independence number and chromatic number, we have nice results, but there are lot more graph parameters, and you can observe what happens to this graph parameters when we apply the operator gamma graphs. Another direction is, for this only I just mentioned that there are variations of domination numbers. There are if instead of gamma sets, if you are taking total dominating sets or independent dominating sets or paired dominating sets or any dominating set of your choice, you can have a similar definition, gamma total graphs. Sets will be total dominating sets of cardinality gamma t, and two vertices will be adjacent if they differ exactly at one position. So similar thing can be done for any graph parameter which you have. I understand that the next session, due to Professor Samir Vaidya, deals with some variations of domination numbers. If you are interested in any of those domination parameter, you can definitely think of doing the same for gamma graphs with that new domination parameter. So that is possible. This 4 types of variations are already available in literature. There are papers published in these 4 directions. Okay. Another branch is graph dynamics. This is for graph operators. If you iteratively apply an operator and consider the graphs obtained, if that collection is finite, then this particular operator is convergent. If that collection is infinite, then this operator is divergent. And if you apply the operator, you get the same graph. Say like gamma dot Kn is equal to Kn, right? If such a property is satisfied, we say that that graph is fixed. And if you repeatedly apply an operator, and finally we reaches the empty graph, then we say that that particular operator is mortal. In the case of gamma graphs, there are situations where convergence applies. There can be situations where divergence holds. There are gamma fixed graphs, but there won't be any gamma mortal graphs, because at each stage the vertex set corresponds to the gamma set, and for any graph there will be at least one gamma set. So the graph is not going to die ultimately. At least one vertex will be left. Okay, so there are no gamma mortal graphs, but there are gamma fixed graphs. And here are some open problems. Of course, the characterization problem of gamma graphs is open. There is a possibility for you to characterize it using forbidden subgraph characterization. You can look for other types of characterizations also. Can iteratively gamma graphs be obtained? Can you give any structural characterization for gamma graphs? All such questions are open. Given a graph, whether it is a gamma graph or not, how to identify, that is open. Then find all forbidden subgraphs of gamma graphs, or any forbidden subgraph of cardinality of order greater than or equal to 7 is an open problem. Recognition of gamma graphs is open. Identify graph classes which are gamma graphs. I already told you that complete graphs, trees and cycles, they are all unicyclic graphs, they are all gamma graphs. So identify such classes of graphs which are gamma graphs. Say co-graphs need not be a gamma graph because K23 is a co-graph and we know that it is forbidden for the class of all gamma graphs. So identify graph classes which are subclasses of gamma graphs. Then find gamma graphs of certain classes of graphs. We have seen what is gamma graph for complete graph, for path, cycle, complete bipartite, like that for co-graphs. For different classes of graphs, we have obtained the gamma graph of that class. Can you do that for other classes of graphs? So these are wide open problems. And if you are interested in graph dynamics, here comes again a long list of open problems. Discuss the closure property of gamma graphs under graph products and graph operators. What is the impact of gamma graphs on graph parameters? And coming towards dynamics, characterize graphs which are gamma fixed, which are gamma convergent, which are gamma divergent, which are gamma periodic or mortal, like that. Such questions are open. Either you can characterize or you can find graph classes which are convergent, graph classes which are divergent. Such questions are all interesting. So these are my major references. There are only a handful of papers published on gamma graphs. So it is a fresh new area where you have a lot of openness. So with that, I conclude. Thank you.
Thank you for the nice lecture. It is for the participants to get any clarification or any observation. You can unmute yourself and you can post the question or any clarification needed. Okay, for the time being, let me have some curiosity. You see, in the co-graph, you are taking complement and the reduction is 2K1 or something last?
Take complements within components. That is the idea.
Components, and then it is getting reduced to?
Reduced to isolated vertices.
Okay, suppose I stop at some classes of graphs, K2.
That is
Instead of
also
isolated vertices, path, or in more particularly, let me stop at a stage, it is K2 plus something. Are there anything of that kind?
I don't think there is any study in that direction. But regarding K2, the thing is that you are reaching a stage where it becomes K2. That means at the next level, it will become isolated vertices.
Yeah. Okay. So not only K2, some cluster of something.
Yeah.
I'm not stopping in some iteration. It will be performed at last, but after some time you will not get anything. Repeatedness occurs.
Yeah,
for example, after isolated
it will be interesting if we are looking for some self-complementary graphs. If we reach a stage where a component is P4, we can't proceed further. And you take complements with them. So instead of K1, you can think of some self-complementary graphs. There is no research work in that direction. So maybe a new good area, sir. Okay. Thank you for suggesting that.
And another thing, when you are applying the operator, you are getting, you said that the complete graph operator is being applied, it is the same complete graph, isn't it?
This particular operator, gamma graph.
This particular operator. Yeah, whatever be the operator. But instead of the same number of vertices, can we reduce the, or we can put it as instead of the same class, can we replace something else?
That is also possible, sir. That comes to the section of characterizing gamma graph of a particular graph class. It can be another graph class also. That is possible.
Can be another class. Instead of automorphism, why don't we consider isomorphism?
Yes, exactly, sir. That is also possible. Work is going on in that direction also.
Are there any work related to this co-graphs and the graphs from groups or rings?
Sir, I'm not... Yes,
any work of that kind?
Graphs generated from groups and co-graphs, they are related. I have seen some papers.
I know the comment of Peter Cameron in that regard. Yeah. Because he is always interested in bringing this graph class to a co-graph.
Yes, sir.
I think so. Okay, fine. Anybody else? Okay, in the absence of any more observations, let us thank the speaker for the nice lecture. Thank you, Dr. Abarna.
Thank you, sir.
Yeah. I think we continue immediately. So it's my pleasure to invite the second speaker of this today's session, Professor Samir Vaidya. I think my part in this introducing the speaker is no more a valid business, because he is a very known academician for all the participants as well as almost everyone in discrete mathematics in India. However, as a formal duty, let me say few words about Professor Vaidya. Professor Samir Vaidya is at present Professor and Head Department of Mathematics, Saurashtra University, Rajkot. And of course, it's my privilege and proud to say that we have got a very good friendship for a very long time. And he has got a very rich experience of 35 years of teaching, and as well as equally good amount of contribution on the part of the research. In his research contribution, he has guided 30 MPhil scholars, and apart from that, 23 PhD scholars, and of course another battalion or another amount of 6 people are doing research under him. It's really a good contribution towards research. And by way of intensive research in graph theory in the areas of domination, labeling, and so on and so forth, he has published a good amount of, not only a very huge amount of 205 publications in these areas, and out of which there are about 1,645 citations. His H index is 21, I index is 56, and his papers on the topic of labelings are very much attracted by various researchers in that field. He is a reviewer of journals like Ars Combinatoria, Utilitas Mathematica, Journal of Graph Theory, Journal of Indian Mathematical Society, Shyam Journal of Discrete Mathematics, and so on, so forth. He is also a member of editorial board of some well-reputed journals in discrete mathematics. So these are all the research expositions of Professor Vaidya. And to his contribution in the academic field, he has been serving as Vice President of Atmiya, Academy of Discrete Mathematics and Applications, an international academic body which promotes the research in discrete mathematics at large in the entire globe. And another important thing is he has been designated as president for the Atmiya from April 2022 for another 2 years. So it's my proud and privileged moment to invite my long associate and friend of mine, Professor Vaidya, to talk on some variants of the class, the parameter of domination in graphs. Please, sir.
Thank you, Dr. Chelvam, for kind words. I am only the beginner in this field. I remember those days when you conducted a conference and I was invited. At that time, it was the beginning of my career. Yeah, it was the beginning of my career in the field of graph theory. And since then, by the best wishes of the friends like you, Dr. Vijay Kumar, Arumugam, my friend Dr. Nitaben, and all the well-wishers, I can record the progress. And what I learned that as a researcher, one has to work without looking towards our wristwatch. And then we can help our student, we can guide our student, and it is the direct service as an academician we can contribute to the society. And that is the thing we have. And what you have spoke for me, it is a little contribution to the society. Now, I will share my content. So, much has been told in the invited talk by Dr. Aparna. It was a very good and informative talk. In the present talk, some of the things will be repeated, and every expert will like that the audience may like it and able to understand. But only one effort will not be sufficient, because the truth will become universal truth if it is repeated and bring into the notice several times. So it is also an effort in this direction. So how the concept of domination and graph theory will become popular, and what is the importance. Now, after the talk of Professor Vijay Kumar, we also know that the concept of graph theory was initiated by Leonhard Euler when he put the Königsberg problem and represented the first graph drawn ever the history of graph theory. But I have seen that in every conference, seminar, or workshop, there are the beginners. And to provide motivation, certain things are always essential to put in the notice of the such target group. Because in every conference or any academic event, the experts are only 10%. The 90% are learners. And we are also the learners. There is no upper limit to acquire the knowledge. And that's why if you feel that certain things are the repetition, then kindly bear with me. With these words, I will like to present my views. This is the plan of my talk. Historical background of graph theory and some milestones, basic definitions, dominating sets, some varieties of dominating sets within conjecture, applications of theory of domination, and references. Then, as told by Blaise Pascal, life is good only for two things: teaching mathematics and discovering mathematics. Most of us are teachers, and busy with research work. So it suits to us, and let us continue to move in this direction. And as told by Bertrand Russell, mathematics passes not only the truth, but the supreme beauty. And that beauty is naturally inherent in graph theory, because the representation of graph is very much aesthetic appealing. And as told by Srinivas Ramanujan, mathematics is beautiful if you can see and appreciate its beauty. And historical background, I will quickly move because much of us are aware with this. So, representation of the conic-Buzbridge problem by Leonhard Euler is supposed to be the birth of graph theory during 1736, and some other milestones are there. So in 1840, the systematic presentation of four-color problem by Mobius in one of his lectures, and theory of trees by Kirchhoff, and systematic definition of trees by Arthur Kelly. So when we look to this chronology, that the concept of trees was applied much before its initiation. So sometimes the use motivates us to introduce certain concepts. And that is the beauty of mathematics. And Arthur Kelly published a paper on four-color problem in first of the volume of Proceedings of Royal Geographic Society. And in 1920, a first book on the graph theory by De Coney. So again, we can look to the beauty of graph theory. That is, the first book was published in 1920, and this year is 2022. In 102 years, graph theory is flourished like anything. In 1958, domination in graphs as a theoretical subject was formalized by Claude Birch, and in 1967, concept of graph labeling was introduced by Alexander Rosa. In 1976, Wolfgang Haken and Kenneth Appel obtained an affirmative solution. As yesterday in the keynote address of Professor A. Vijay Kumar, he mentioned that the proof was computer aided. Then the graph is a structure with two sets, an edge set and a vertex set. And the elements are called vertices and edges respectively. And the cardinality of vertex set and edge set is known as order and size of graph G. And the subset of a vertex set and edge set, if we consider and prepare a graph, is known as the subgraph. And the neighborhood, I will skip this definition as Dr. Aparna has already covered this thing. To manage the time, I will skip certain things. Then degree of a vertex, because I need that thing in my discussion. So degree of vertex, the number of edges incident to vertex. And minimum degree we denote as delta G, while the maximum degree of a graph G will denote as capital delta G. So again, we go back to the historical background for the initiation of the concept of a dominating set. Then dominating set appears to have its origin with the game of chess. And in 1862, D. Janisch considered the problem of determining the minimum number of queens to cover all the 64 vertices of a chess. And according to the game of rules of chess, as well as in the real world, queen can move anywhere, not only on chessboard, but anywhere. And that is why, so queens are attacking or non-attacking, that we can see here in this chessboard. These 5 queens are attacking, and in other arrangement, these are non-attacking, but minimum 5 queens are needed to cover all the 64 squares of the chessboard. And the connection between chessboard problem and dominating set in graph is immediate. The 64 squares of a chessboard are the vertices of a graph, and 2 vertices are adjacent in G if each square can be reached by a queen on the other square by a single move. And the dominating set of vertices, subset of a vertex set, is called a dominating set if every vertex in a vertex set is either an element of vertex subset S or adjacent to an element of S. And naturally, we as a mathematician always look for the minimal dominating set. And the minimal dominating set is subset S is called a minimal dominating set if no proper subset is a dominating set. And we denote it as MDS. Here we have a graph and it is a minimal dominating set of cardinality 3. It is blue color vertices form a dominating set of cardinality 4. And here the minimal dominating set of cardinality 5 is shown. And some other terms are introduced here. They are enclave, isolate, and when a set is said to be enclaveless, if it does not contain any enclave. And we can also say that a vertex V of S is isolate if V is not adjacent to any vertex of S. And in this figure, which we have considered, 3, 6, 7, 8 is an isolate, 6 an isolate of S. While if we consider the set S with 4, 5, 6, 7, then 5, 6, 7 are the enclaves. So there are some equivalent definitions depending upon the definition of concept of neighborhood set of S, that if the closed neighborhood set S is same as the vertex set, then we say that S is a dominating set. And if equivalent is saying that if V minus S is enclaveless, then we say that S is a dominating set. Then some remarks are done for the advancement of the discussion. Every superset of a minimal dominating set is a dominating set. Once the minimality is established, then it will be there. And set S is minimal with respect to property P if every proper subset of S does not have P and every superset S having the property P. And the property is said to be maximal if every superset of S does not have that property and every proper subset of S having that property. So the domination number is denoted as gamma, and it equals to the minimum cardinality of a minimal dominating set of G. Or we can have the definition of upper domination denoted as gamma G, capital gamma G, equals to the maximum cardinality of a minimal dominating set of G. And the first 3 theorems proved by R in his book, Theory of Graphs, they are stated here, just for the sake to make this presentation a compact one. They are stated here. So a dominating set is the MDS if and only if U is in isolate and there exists a vertex set U of V minus S for which the intersection of neighborhood open neighborhood of V with S is a singleton set. And every connected graph G of order at least 2 has a dominating set whose complement is also a dominating set. So it established the relation between the dominating set and its complement. And a graph with no isolated vertices, then the complement V minus S of every minimal dominating set is a dominating set. Also, after such fundamental discussion and conceptualization, we move to the discussion of some varieties of dominating sets. Then cycle dominating set. If vertices of dominating set form a cycle, then it is called a cycle dominating set. And Aparna has also introduced the concept of total dominating set. So if the open neighborhood set of S is same as the vertex set, then we say that the S is a total dominating set. Here we consider the Peterson graph and the vertices 1, 2, 5, 6 is a total dominating set, while the vertices 1, 2, 3, 4, 5 form a cycle dominating set. And correspondingly, its cycle domination number and total domination number are respectively 4 and 5. It is shown here. And now the independence number, that S of vertex subset S is called independent if no two vertices of S are adjacent, and it is a independent dominating set we consider if it is dominating also. Then independence domination number denoted as IG is the minimum cardinality of an independent dominating set. Here we have the graph and the independent domination number is G is 3. Then any superset of a maximal independent set is not an independent set because it is the maximal property. In other words, an independent set S is maximal if any vertex set properly containing S is not independent. And an independent set is a maximal independent if and only if it is independent as well as dominating. And every maximal independent set in graph G is a minimal dominating set of G. And this is the domination chain where these parameters which we have introduced lies between the domination number and upper domination number. Then we have equitable dominating set. What we learn, once we have the dominating set and add some other properties or characteristic, then it gives rise to a new domination model. Once you have the better, one can prepare dosa, idli, uttapam by just adding some more ingredients. The same theory applies here. So once we know the concept of domination, we can discuss other variants and varieties of dominating sets. So a subset D of a vertex set is called an equitable dominating set if for every V of the complements of D, there exists a vertex set U, a vertex U of D such that the degree difference of the end vertices of any edge is at most 1. Means for how it is useful. Why? What is the motivation behind? that this concept is useful to distribute the resources equally, almost equal. And the minimum cardinality of such dominating set is called the equitable domination number, and it denoted as gamma Eg. And the concept of minimal equitable dominating set is analogous to the MDS, which we have already introduced earlier. And for the better understanding, we consider the cycle C8 and the molecular vertices form equitable dominating set, and the cardinality is 3. This concept, the concept of this was introduced by Swaminathan and Dharmalingam. And this is the necessary and sufficient condition for a set to be an equitable dominating set. And these two results, why I have stated the first results proved by Orr in his first book, Theory of Graphs. Then the new model or new types of new variety of dominating sets, the people always try to develop a structure for the further discussion. And these two results are just analogous to the first result proved by Orr. And now, this is a very important variation, an important variety of a dominating set. It is global domination, and it is a frontier between a graph and its complement. So let us see it. What is complement? The complement G bar of G is the graph with the vertex set V, in which two vertices are adjacent if they are not adjacent to each other, and the global dominating set. It is just not the exercise to find the dominating set of a graph and the dominating set of the graph complement. No, it is not like that. But all the vertices will dominate in the graph, the same vertices will dominate in its complement. And that is the importance. And again, we can experience the beauty of mathematics, that the same concept was introduced by Sampat Kumar, who coined the term global domination, and Brigham and Dutton in 1990. And they used the term fact domination. But in the present time, the concept is popular as global dominating set. As I told you, the problem is whether the same vertices will dominate in the complement or not. And here, to visualize the concept, the graph C5 is considered, and its complement is also there. And the same vertices V1, V2, V5, they are dominating in C5 as well as in its complement. So the global domination number is 3. The global domination number is 3. And the global domination number of some standard graphs are shown here. And for the tree, Sampat Kumar proved that the global domination number of tree lies between this range. The same results also there. analogous results also there for the domination number. And now we add one more property, one more characteristic in global domination. And it gives rise to a new concept, which was introduced by Baswan and Telly recently in 2015. And it is the global equitable domination number. So the construction of definition and the concept of global equitable domination is quite analogous to the things which we have introduced earlier. So I will skip it. And the global equitable domination number of some standard graphs are stated here. And now I will like to move on our own contribution in this regard. That is the congruent domination. It has some encounter with number theory. A dominating set D is said to be a congruent domination if the degree sum of vertices of vertex set is congruent to modulus means of this degree sum of vertices as 0 mod this, congruent to this. So it is little stronger thing because it requires to have some basic things of number theory also and congruence modulo. And analogous to our earlier definition, we can have the definition of congruent dominating set as well as congruent domination number. We used the notation gamma CDG and independent congruent dominating set. The independentness we have already introduced. If we add that characteristic between or the relation between two vertices, then it gives rise to a new type of dominating set. It is known as the independent congruent dominating set. And at least one vertex is essential. So the lower bound is this. And if all the vertices are needed to dominate the graph, then naturally the equality will be there. Hence, we have this. That is 1 less than or equal to the congruent dominating set less than or equal to n, and both the bounds are sharp. Since every congruent dominating set is a dominating set, we have this, and we know the domination. This is, again, it is a basic theorem, fundamental theorem in the theory of domination, and where our new type of domination number lies, it is shown here. And there are the graphs which achieves this bound. It can be also shown. And what we have proved here, for a connected graph G of order at least 2 has congruent dominating set T, whose complement is also a congruent dominating set, but it is a necessary and sufficient condition if and only if this condition holds. And again, if the graph is Eulerian with summation is 2p, where P is the order. For all, particularly when P is prime and G is not the cycle C3, then gamma CD is equal to N. So in this way, we have proved this result in the context of the concept of Eulerian graph. Every maximal independent congruent dominating set is a minimal congruent dominating set. All these things are developed, proved in connection of the analogous results exists for dominating set. For cycle, these are the things, and it is demonstrated here for C8, for path Pn. It is also demonstrated here by considering the example of P9. For complete graph, it is 1. It is shown here. While for complete bipartite graph, it is 2 if n or m, or n equal to m, or n equal to m into m minus 1, or m otherwise. And it is also demonstrated here. Then for star graph, it is 1. It is shown here. And Wissing's conjecture, because any discussion in graph theory remains incomplete without any conjecture. For any graphical invariant sigma, a graph product, it is submultiplicative if gamma g cross h is less than or equal to gamma g into gamma h. If inequality reverses, then it is supermultiplicative. And if the equality holds, then this property, this invariant, called universal multiplicative. And the domination invariant gamma is supermultiplicative, means the greater than or equal to for this Cartesian product, and that is the Wissing's conjecture. And still it is an open conjecture, not settled. We have an example of it. We consider two graphs, C5 and K2, and it is the Cartesian product of this. And you can see that gamma, that is domination number of C5 cross K2 is 3, while the domination product of their domination number is 2. And many efforts has been carried out to settle this conjecture, but for the particular situation or for particular graph families, it is studied. So here is the list of these efforts. So now, for the concept of global equitable domination, we have studied this. It is submultiplicative on the Cartesian product G cross P2, where G is equal to Pn or Cn, while it is universal multiplicative for P6 and C6. So it is shown by help of this coordinate graph. And domination coloring is 5 minutes are in my hand. So I will move quickly because it is again how we can discuss, we can relate this two potential concepts. That I will skip the basic definitions of coloring because they are well known. Then the concept of dominator coloring is there. A proper coloring is called dominator coloring. If each vertex of a graph dominates every vertex of some color class, then it is called a dominator coloring, which the concept was introduced by Gera and others during 2006. And analogous to the definition of chromatic number, the dominator chromatic number is there. It can be seen here. And some important results are there by and others. Then applications of theory of domination, where we have to allocate the resources, then it is very much useful for the transportation problem or for the solution of any network. It is there. So for radio and TV network, and for defense and surveillance, and for RD configuration, if we have R resources to allocate at distance, the minimum distance, then the concept of domination is very much useful. And global equitable domination is which is very much useful in the allocation of resources almost equal. Like
paper presentation schedule on update culture la ಏನು ಇಲ್ಲ ಅಂದ್ರೆ ಚೇಂಜ್ ಏನಿಲ್ಲ ಎರಡು ಸೇಮ್ ಅದಲ್ಲ.
Please unmute yourself. There's some other voices there, please. So if the existing links fail, then what happens? Then in that case, the global domination is very much useful to establish the network again, restore the network. And these are the references. And I would like to point for all the beginners that if just you have listened, then you will necessarily forget it. And when you have seen the concept of domination several times, then you will really remember. But to work on the concept which are already discussed and are going to be discussed in the remaining 2 days, then you have to put on the piece of paper, then you will really able to understand it. And with this one, I am very much thankful for to the organizing committee of this 3 days national conference organized by Hemchandracharya North Gujarat University in association with the Atmiya University. I am very much thankful to them and also thankful to all the participants for their patient listening. Thank you.
Thank you, Professor Vaidya, for the exhaustive coverage of the literature with regard to domination and various variant or various domination parameters related to classes or the entire graph classes. Participants, please, you can seek any clarification or anything you wanted to know about. Put forth the question by unmuting yourself. Please. Anybody? Okay, in the absence of any more clarifications, let us thank the speaker for the nice exhaustive expository talk on domination and various variants. Thank you, Professor Samit Vaidya.
Thank you. Thank you.
Thank you, Shailavam sir, for hosting this and for chairing this technical session. And now I would like to invite Father Joseph Verghese for chairing the next invited talk. Father Joseph Verghese sir is a professor in Department of Mathematics, Christ University, Bangalore. He has completed 5 PhD supervisions and 8 MPhil supervisions. He has also published 105 research articles in various national and international journals. It's lovely to have you here, sir. I hand over the session to you now.
Thank you, Aditi. It's a rare honor to be part of this conference, and not just being part of this, to introduce a person like Professor Nita. You're going to listen to one of the versatile figures in operations research in India. Last 30 years, she has been doing great works, great strides in the field of operations research and related areas, convening conferences, keeping up the promises, maintaining teaching, as well as moving around several venues for invited talks. She has already completed more than 100 invited talks in India and abroad. In Scopus alone, Scopus Index journals alone, she has more than 200 research articles. She has a total of close to 400 research articles and 20 books. Adding to all this, she had guided 30 scholars to their PhD. As an organizer, I have a very memorable experience with Professor Nisa. The way she convened the Gujarat Conference of Applications in Mathematics. All of us were treated elegantly with such a pleasant hospitality. And she has, exactly as a teacher of operations research, how to optimize timing as well as finally delivering the materials on the venue as well as after the conference was over. The work came out as a Taylor and Francis book, which is unimaginable in a lightning speed. She is currently the council member of Indian Mathematical Society, and she has been serving as the Vice President of Operations Research Society of India. Apart from all these extra works, extended works, she is also the head of the Department of Mathematics at Gujarat University and a senior professor there. It's really wonder how a single person, a woman, can do all these works. If I can name someone as woman, it's a rare honor. Let us listen to this wonderful person. Professor Nita Shah, please. Ma'am, it is to be unmuted. Chirag sir, could you check? Yes.
Hello, Nita madam.
You can hear. Ma'am, is it?
Manoj sir, please make Nita madam presenter. Madam, please unmute your mic. Your mic is mute. Now your mic is unmuted.
Now it's clear, ma'am. Oh, still it is.
Madam, your voice is very. Madam, your voice is very low. Might be some problem with your mic. You please rejoin if it is called. Let us wait for 2 minutes. We will be rejoining.
All the other participants, kindly mute your mics.
ಆಕತಿ ಆದ್ರೂ ಅಷ್ಟು ಸರಿ ಬರ್ಲಿಲ್ಲ ಅದ ನಾ ಡೌನ್ಲೋಡ್ ಮಾಡಿ.
Hello, dear participants, kindly mute your mics.
200 MB.
Check your mics kindly.
ಚೆಕ್ ಮಾಡ್ರಿ ಆನ್ಲೈನ್ ಬಂದ್ರ ಇದ್ ಮಾಡ್ರಿ. ನಂಗೆ ಸ್ವಲ್ಪ ಇದು ಅನಿಸ್ಲಿಲ್ಲ ಕಂಫರ್ಟೇಬಲ್ ಡೌನ್ಲೋಡ್ ಮಾಡ್ರಿ.
Could you kindly mute your mics?
ಏನಾಗೈತನ ಅದಕ್ಕೆ ವ್ಯತ್ಯಾಸ ಹೋಗ್ಬೇಕು. ಅದಂತಾನೆ ಅದ್ಯಾಕೆ ಕಳ್ಸ್ಯಾರನ? ಯಪ್ಪ ಏನ್ ಕೇಳ್ತಾರ ಅಂದ್ರೆ ಕ್ವಶನ್ ಯಾಕ
Hello. Varghese sir, am I audible?
Yes, perfect. Perfect.
Okay. I'm sorry for this inconvenience. I'm sharing my screen. I'm sharing my screen.
Please.
This one. Is screen visible?
Yes, ma'am.
Okay.
Full screen.
Yeah, full screen it is.
Correct.
Okay. Good afternoon, Father Varghese. After 2018, we are meeting virtually, but nice to see everybody. And thank you, organizers at NGU and Atmiya University. As Father Varghese said, I am basically a researcher in operation research. So obviously, I grabbed this scenario to explore transportation problem using graph theory. And that's the reason why title of my talk is Transportation in Networks. Transportation network means by just a minute.
ನಮ್ದು 5 ನ 6 ರೀ 5 ನ
Transportation network means by which commodities are shipped from the production centers to their markets. This is basically a very simple problem which almost all PG students learn about, that what is transportation problem. And what exactly we do most effectively, we want to have the allocation. And here, when they are viewed as a digraph. So as Dr. Apana said, applications, and Professor Samir Vaidya said in the last part of his talk about the application. So basically, I will be presenting application of digraphs in transportation, that is allocations. So a network N is a digraph D with two distinct subsets of vertices X and Y, and a non-negative integer valued functions C defined on its R set A. The sets X and Y are assumed to be disjoint and non-empty. Non-empty is obviously because we want to have some allocations. The vertices in X are the sources of a network problem, that is a transportation problem, and Y are sinks. That is what we do, what we have in transportation problem, source and sink, or source and destination. So they correspond to the production centers and markets respectively. Please unmute yourself. Please mute yourself. Vertices which are neither sources nor sinks will be labeled as or called as intermediate vertices, or you can say pendant vertices. The set of such vertices will be denoted by I. C represents capacity of the network, and value on RC is how much capacity can be given from source to destination. This capacity is acting as a nominating number, and capacity of an R can be thought of as representing the maximum rate at which a commodity can be transported along that particular route. So this is how it looks like. You have a network with two sources, say X1 and X2, and three sinks, Y1, Y2, Y3, and four intermediate vertices, V1, V2, V3, V4. So this problem can also be treated as a transshipment problem where sources are sinks and sinks are sources. That is vice versa. Okay? Now, a frame or a flow in a network N is an integer value function F, which is bounded by the CA. What FA represents the rate at which material can be transported along a route A, and C is the capacity constraint. That is what we call as a maximum resources which can be allocated from source to sink. And obviously, This imposes a natural restriction that the rate of flow along an arc cannot exceed the capacity of the arc. Now this F minus and F plus are denoted as conservation conditions. That is what we call in operation research transportation problem as Ream conditions. Just be careful that every network has at least one flow. That is, it can be transported from source to sink. Since the function f defined by f of a is equal to 0 satisfies both the conditions which was stated above, and this is called zero flow. So in OR we call it Ream conditions. Here in the graphical results, that is in optimization, through graphical results of a transportation problem, we will call zero flow. Now let us have subgraph. That is, if S is a subset of vertices in a network N and F is flow in N, and the resultant, that is what we call as how much is left, is called the resultant flow out of S. And F minus minus F plus is called the resultant flow into S. That is, it can be transported or it cannot be transported from the destination sources. Now, conservation conditions should always be satisfied. So, the flow out of any intermediate vertex is 0. And it suggests that the resultant flow out of X is equal to resultant flow into Y. This allocation should be satisfied demand and supply wise. So, the condition, common quantity, which is called the value of F, and we denote it by VALF, is given by difference of how much can be given, that is F plus X, and how much can be received by the destination, F minus X. That is what we do as a difference when we allocate it. So here we have same figure I will be continuing in my talk, which I had given in the first table. So what if you just use F plus minus F minus, the difference of incoming and outgoing demand and supply condition, we have the value of the flow to be 6. Here, X1 and X2 are the sources and Y1, Y2, Y3, Y4 are destinations. Okay. A flow F in a network is a maximum flow if there is no flow, say F dash in N, such that value of F dash is greater than value of F. And this flow are of importance in the context of transportation network. That is, I cannot allocate more than what is between the minimum of or maximum of demand and supply. So we want to have the problem of determining maximum flow in an arbitrary network. Can be reduced to the case of network that have just one source and one sink by means of a simple device. That is, and this is what it should follow as a rule. You are given a network N, we construct a new network N dash by satisfying Ream condition, or in this case constraint condition, so that zero flow can be maintained. It should have adjoin two new vertices X and Y to network N, original network. Join X to each vertex in capital X by an arc of capacity 0. That is, you cannot have demand and supply. Join each vertex in Y to small y by an arc of capacity equal to 0. And designate X as the source and Y as the sink in new vertex. That is in new network. So we had original network. We use demand supply condition and try to have the equilibrium between demand and supply and having a new network N dash, and then follow your northwest corner method or Vogel's approximation method or minimum least cost method. Okay. So here we have same figure is written here. This 3 infinity means we cannot have, and now we don't have any demand or supply to be met. Okay. Now flow, so we have now two flows, N and N dash, okay, correspond to one another in a simple way. If F is a flow in network such that the resultant flow out of each source and into its sink is non-negative. Then we can define new function, say f dash, as allocate if A is an arc of an n, difference of f plus and minus f minus, that is demand and supply, if A is A joining vertex x and v, and have the difference of supply and demand if A is the A joining v and y. So now we have f dash A as a flow in n dash. Okay. F is flow in network, original network. After satisfying demand and supply of single source and single destination, we have a new network f dash, and its value of the function is given by this. And one can check that value of f dash in n dash and value of f in n will remain same. So now, next we need to have cuts. If you have a network n with a single source x and single sink y, then a cut in n is a set of arcs of the form S minus. Minus is just the notation, or I can say S dash, where x belongs to S and y belongs to S dash. The capacity of the cut K is the sum of the capacity of its arc. So collect all the capacities of A, that is C of A, and then sum it up. That defines the capacity of the cut K in network N. So here, bold line, this bold line defines the cut of the problem which we started with. And that is nothing but the, one can say that this is critical path. That is, it gives optimum solution to the transportation problem. So here, using graph, we have a cut method to find the optimal solution of the transportation problem. Okay. And for that, I need the lemma that for any flow F and any cut S dash in network N, value of the function is given by difference of demand and supply. And arc A, F0, if and only if Fa equal to 0, it is positive, that is you can have allocation. If Fa is greater than 0, F is unsaturated if demand at particular point A is less than what you have, and it is saturated if demand and supply or demand and resources are equal. That is, you can give them, you can allocate it. And using this lemma, we have a theorem that for any flow F and any cut K, say S dash in N, value of F is bounded by capacity K, where capacity is sum of the CS. And this also holds, that is equality holds, if and only if each arc in S dash is F saturated. And we know F saturated is Fa is equal to Ca. Otherwise, it is 0. Okay. And unsaturated will never happen because you have to satisfy Riem conditions or zero flow in transportation problem. A cut K in N is a minimum cut if there is no cut K dash in N such that capacity K dash is bounded by capacity of K. And F star is a maximum flow and K is minimum cut. Then I can say that value of F star is bounded by capital K. It can even not be equal exactly. Okay. So we have a corollary that if F is a flow, K is a cut, such that value and cap are equal, then it will give you a maximum flow and K is a minimum cut. So here is a trade-off between maximum flow and minimum cut. So it gives me a intuition that I should have a relation between maximum flow and minimum cut. which is known as maximum flow minimum cut theorem. And it says that you have a flow in network, say F, with each point path in N, we associate a non-negative number, IP, defined by minimum of IA. And what exactly minimum of IA is? CA minus FA. CA is maximum what you can allocate, and FA is the allowable demand or supply what you have when you are moving forward. Okay? And if it is reverse, that is, if you don't have this condition CA minus FA to be positive, then I should allocate only F of A to the IA. So IP is nothing but the largest amount by which the flow along the path P be increased. Obviously, you have to keep in mind that value of it should be with reference to relative function without violating Riemann conditions. So now I can say that whether path is F-saturated or not. Path turns out to be F-saturated if IP is equal to 0 and it is unsaturated if IP is greater than 0. Or equivalently, I can say that if each forward arc of P is F unsaturated and each reverse arc of P is F positive. Positive means it is equal to 0. That is, you can always have allocation from the source to the sink. And F unsaturated path is one that is not being used to its full capacity. So something is left with you, and that is not advisable. So an F incrementing path is an F unsaturated path from the source X to the sink Y. That is, some demand or some supply are getting unsatisfied, and that results to the F unsaturated path. So here we have a same example. I constructed with X and Y to be sources and V1, V2, V3, V4 to be sinks. So we have one F incrementing path defined by X. Bold line you have to see X, V1, V2, V3. And the forward arc of the path PR is given by X, V1. One thing, and second one is given by V3Y. So when you have path PX, that is incrementing X, V1, V2, V3, your demand and, or I can say Riemann conditions are getting satisfied. But when you move towards or move forward, then some demand or some supply remains unsatisfied. That you can go, because this is just we have considered single source and single sink. And that gives me one more result, that a flow F in network N is a maximum flow if and only if N contains no F incrementing path. So Riemann conditions should get satisfied. That is what physical interpretation of this result is. Then we have one more result, which is talking about the minimum cut. That is, if in any network, the value of a maximum flow is equal to the capacity of the minimum cut. So we need to balance between demand and supply so that we can have allocation which satisfies Riemann conditions. And that is the reason why the theorem, which was stated as a theorem 1, we call it maximum flow and minimum cut theorem. This is, in fact, the central importance in the graph theory. Proof is constructive in nature, that is, go on adding nodes as a source and sinks as the allocations, and continue to extract from algorithm to have the maximum flow in a network. And this algorithm actually has given rise to labeling method, because here what you will be allocating are the labels, okay? And that was given by Ford and Volkskrant in 1957. And now thousands and thousands of different labeling methods are available. And I'm happy to say, being an Indian, I'm happy to say that maximum labeling methods are getting generated by Indians. So starting with a known flow, for instance, the zero flow, it recursively constructs a sequence of flows of increasing value, and at some point of time, it terminates with a maximum flow. So after the construction of each new flow, a subroutine, so in graph theory, we can say subgraph, called the labeling procedure, will be used to find an F incrementing path if exists. Not necessary that every time you will able to find F incrementing path. If such a path P is found, then revise flow based on P, that is revise F1. Okay? And that can be constructed and taken as the next flow in the sequence. So that is considered as the maximum one, and then that part stops, go with the next flow. If there is no such path, the algorithm terminates and we get a maximum flow. That is F turns out to be the maximum flow. And here we have the simple flow chart I am giving you. Labeling method, what we do, we have L as a set of label vertices, S as a set of scanned vertices, and L of U, that is set of vertices labeled during scanning of U. Here scanned means when allocation is done, that has to be striked off or have to remove from the list. So we scan them, and but before we scan, we need to allocate. So we say that that particular vertex has been labeled during the scanning process. So this is how labeling can be done using source and sink in transportation problem. But when I say that I have flow, I also need to have some characterization for feasible flow. Let N be a network, and flow will be said to be a feasible if difference is bounded by h of xi for all vertices xi in the network. And if it is greater than the difference, that greater difference should be bounded by how much we can label it. Okay? So flow F is feasible if the resultant flow out of each source xi relative to F does not exceed the supply, and the resultant flow into each sink relative to F is at least as large as the demand of that particular destination. So my planning was to say that, in fact, at least to give you idea that how graph, or in particular here digraph, can be used for solving transportation network. I said transportation network, but Professor Vaidya already said that it can be done for communication network, it can be done in cabling. Why to go for communication and cabling? Even our electricity, what we do circuiting in our own offices or our at home, digraph, application of digraph can be done. So this is what I wanted to share with you in operations research.
Ma'am, it was a pleasure listening to you. See, it is a rare honor, capacity as well as expertise to connect two different disciplines, which are sometimes treated as independent, but have almost the same approach, same expectations, optimizing a given situation, modeling properly and optimizing. See, most of us have been learning and teaching transportation networks for long. Of course, we sometimes get the feeling that it is also a labeled or weighted graph. However, presenting that typically as a graph theory problem, and graph theory problem turning to an optimization problem that can be treated under operations search, this is a new opening for many of us. Ma'am, thanks for enlightening us, especially the simple way of presenting Maxwell-Mincut theorem. identifying the min cut, and then this augmenting path and F augmenting path. All these were actually very easy once when you presented through the graph theory terminologies as well as labeling methods. And now I invite the participants as well as the listeners to interact with the ma'am. Please raise your questions.
Mukti, sir, Mukti madam wants to ask something. But
Yes,
she
ma'am.
needs to be unmuted.
Yeah, it's okay. They have done it.
Oh,
Okay.
hello, madam. How are you?
I'm quite okay. Thank you very much for your nice talk.
Thank you.
But I have one just my understanding. If I talk in terms of graph theory or digraphs, we have verses which have sources.
Madam, your voice.
Hello, are you able to hear me?
Yeah, be very close to the mic, ma'am.
I'm very close. This one.
Okay. Go ahead, ma'am.
Okay. Are you able to hear me?
Sometimes you are losing the strength of the voice. Maybe it's a transportation issues. We can start using your
Okay, no problem.
data transfer issues.
If I take a set of verses which are our sinks, then there a connection between any two sinks? That is a arrow line from one sink to other sink?
Madam, it can be done, and that is what I gave you in the first figure. That refers to transshipment problem. Sources and sinks, if you don't differentiate, then also it can be applied.
It can be applied.
Yeah.
It is generalized transportation problem. Then it becomes transshipment problem, ma'am.
Yeah.
But usually in transportation problem, your source and sink, they are independent sets.
I agree.
Yes.
I agree. But you can also do it for transshipment problem.
Okay. Madam, there is a concept of Petri nets.
I'm still learning, madam, Petri nets.
I think because the people are doing wonderful mistake, because transportation network, they want to attach sine graphs to transportation networks, where I say it is not possible, because one, the thing things are taken from one side to other, how that edge can be negative? Its capacity cannot be negative. So I have seen many papers giving the applications of transported graph theory and networks and other things, where I don't agree at all. But Petri nets is a dynamic structures. There we can, I think your transportation and Petri net, they can be merged in a proper way. People are trying to merge, but later on they leave everything, they take the underlying graph and study. That does not have, that is what you can say, you can just throw it in the dustbin, because you are going away from the transportation. That's all. Thank you very much.
Thank you, ma'am.
Thank you, madam.
Thank you, Anika.
More questions, please. Anyone else? Ma'am, during this lockdown, you have published so many papers related to the problems, especially associated with the COVID-19. So how did you connect your operation search ideas, mathematical modeling with this pandemic situation? And it's...
Sir, I have connected graph theory, operation research, and dynamical system for the COVID-19 transmission. And operation research in terms of medical equipments and facilities which a hospital gives, okay, and how much they should be ready with as an optimum, you can say PPE kit or medicine. That has been done using optimization technique, and even we had used graph theory for optimizing ambulance network. Because when a patient was in need of oxygen, they had to rush to the hospital within 32 seconds. Okay, once they enter in the hospital. Okay, and that has been done using graph theory network.
So here the medical facilities all would come as a sink, and then people affected as sources. Do you use that? Or?
Yeah.
Okay.
Yeah. And it turns out to be multi-scaling optimization, because a huge number of patients and very few things.
Was there a role of transshipment also in that, in case there are temporary facilities, or we can treat medical care on the way?
In fact, we had not considered, but one paper is going on which says that quarantine at home or quarantine at medical centers, temporary centered medical centers, may turn out to be a good one. That is at least a relief to the patient.
Okay. What is the size of nodes you have considered?
Size could not be considered because it was considered as an infinite, because you never know how many patients will turn up per hour. That was taken as infinite.
It's pure theoretical, or you had some simulation, some it's actually verification as well as simulation?
Yeah, we had simulation. If you recollect, Gujarat University had set up a temporary medical hospital, DRDO. And we took data from there and got it simulated to graph theory.
Participants, any questions? I'm not seeing any. Yes.
But everybody must be interested. Even I am interested to whether this COVID-19 will be over or not.
It will get over, madam. It will get over by March end.
March end.
Yeah.
Why I'm asking, then I can come out from my house.
I can't say anything about Karnataka, huh?
At least I can visit Christ University.
Initially, we thought actually, ma'am, going to Chirag's place, even though it was planned for online system. I promised also IDSR that we would be meeting there, but unfortunately, it was extended. But we must meet soon.
That is there now. It is already.
No, Father,
2 years are over. Going to be over.
Yeah, it's almost 2 years now.
Sitting here and there, looking here. But anyway, our minds are working because we don't need any lab and other things now.
Yeah, that's the beauty of mathematics.
Computers are there. Other things, that is sufficient, I think.
Mukti madam, you are very active. You are attending each and every event.
Try my best.
So you are not stuck at home.
But only that I am afraid they should not become angry with me when I give my thoughts on their talks.
Not at all. Not at all. Not at all. We are happy to get the suggestions. And madam, if they are not happy, that means that is their problem, not our problem.
The same thing. See, once I was attending a 2018 one conference. Of course, it was not online in Bangalore University. So I was, I had to go at that paper presentation. I was the chairperson. So they gave me a list having 8 people. Okay. So when the presentation started, I get the other list. There are only 3 people. Then I asked the convener, what happened? This is why from 8 you have made 3. He said, madam, some people requested they don't want to present in the session where Mukti Acharya is the person. Then I told I'm happy because I don't have to spend so much time, but I'm not the loser.
True, ma'am. True.
I'm not the loser. If they ask questions and other things, they will get new this thing. Because with Christ University, I told I will not take the classes. But I don't mind to interact with the research scholars.
Mukti madam, take it other way around. Take it other way. The participants wanted to save your energy.
That's what I do the same way. That's what I can enjoy the time having cup of tea and roam
That
here
is
and
what
there
that
and
is what
eat
I say.
all
Take it
and see
positively.
what the things are there in the lunch and other things now. So that way,
Take it positively.
it was I took in a positive sense only.
Okay, ma'am. Okay. Ma'am, I think there are no symbols of any more questions. Thank you from the bottom of our heart. It was an excellent talk. Kindly continue to enlighten the people who are interested in Operation Search or graph theory in India and abroad. We all appreciate your great contribution to operations research area, especially in the optimization field. And this is one robust area where people are actually looking forward to, even in government as well as private agencies, for efficient transportation network models. Thank you very much for enlightening us today, and we look forward to more works from you. Aditi?
Yes, sir.
Thank you.
Thank you very much, sir, for hosting and sharing the technical session. Thank you, Neeta ma'am, for the talk. And now I think we should take a short lunch break. And the next session will commence at 2 p.m. Yes, sir?
15, I think.
Yeah.
Okay, 2 p.m. Yes.
2 p.m. So we'll be joining by 1:55 p.m.
Aditi, group photo.
A group photo.
Group photo, yes. We'll just take a group photo. Everybody just switch on their camera so that I can a group photo. Yeah, just 1 minute. Yeah. Yes, sir. One second.
Srimali sir is here.
Yes, he's there.
Good afternoon, sir.
Good afternoon. Good afternoon.
Good afternoon to all.
Afternoon.
Okay. Done. So, okay, we'll meet later at 2 p.m.
Okay, have a good lunch.
Yeah. And then the parallel sessions will commence. Welcome back, everyone. Hope everyone had a great lunch. And now I'll be requesting Mukti ma'am to chair this next session. Professor Mukti Acharya ma'am currently serves as a visiting researchman at Christ University, Bangalore. Before, she has served as a professor at Delhi College of Engineering. She has published 81 research papers and one book chapter. Under her guidance, many students have done their PhD. She's managing editor of Indian General Discrete Mathematics. She also has submitted 9 research papers for publication. And it's an honor to have you, ma'am, to chair this session. So I'll hand over the session to you. Yeah. Ma'am, you're mute. Ma'am, we can't hear you. Could you unmute yourself? Ma'am, I'm still, just unmute yourself once. Ma'am, we are not able to hear you. Could you just unmute yourself once?
Now it is okay.
Yeah. Now we can hear you. Yes,
It
ma'am.
takes some time, I don't know. The morning also.
No, ma'am. It's just sometimes.
Thank you, Aditi. And I'm happy and I'm very thankful to you people for giving me an opportunity to chair a session and which R.T. Pandey is a very, I will say, I know her when she was doing MTech, I think, at IIT Delhi. So thank you very much for this one opportunity. Now I just speak few words about Dr. R.T. Pandey. Dr. R.T. Pandey has, at presently, she is working at IIT Ropar as an assistant professor. She did have a BSc from Kanpur University, some CJSJM. Then MSc, MTech, and PhD, all 3 degrees are from IIT Delhi. She completed her PhD in 2016. So her most interest work are in, she is interested in logarithm graph theory, in particular IC and domination parameters. And she has, she was doing PhD, she has SRF as well as JRF. So far, she has published 8 plus 11, 90 research papers, and 8 papers I think are in Scopus SCI journals. And she has a collaboration with Professor Hani, Tom Clocks, Anil Maheshwari, Professor Tetali Prasad, and Vigal. And her wide interest connecting computer science and graph theory. And I request her to take over start the lecture. Thank you, Aarti.
Thank you, ma'am, for giving a nice introduction. And I would also like all the organizers for giving me this opportunity to present my research works. So is it okay? My slides are visible. Am I audible?
Yes, it's okay.
Okay, so here I will be talking about algorithmic aspects of pair domination problem. So basically, I have worked on domination problem as well as some more parameters on domination. And this is one of the very important parameter. And recently, I have done some work with my student and Professor Clocks and Professor Wang. So here, first, I will just state what is domination. So I will briefly explain because you all must be knowing about it. Then I will explain what is pair domination. I will present some of the literature for pair domination, and then I will present some recent results which we have obtained. So these recent results got accepted in a conference, and the paper is also available on arXiv. So we still need to submit it in a journal. So it is very recent work. Then I will also talk about one more variant of paired domination, that is semi-paired domination. So if time permits, I will talk about this domination parameter also. So what is a dominating set? For a given graph, a subset of vertex set is called a dominating set. If every vertex which is not in this set is adjacent to at least one vertex in this set. So for example, if you take these two red colored vertices, then they form a dominating set. And the problem is
Aarti ma'am, your voice is inaudible. I think there's some there is yeah.
He is facing low bandwidth problem in that place.
Yeah, actually it's because of the internet issue. Ma'am, you're inaudible, ma'am. I think ma'am, you're inaudible. You've unmute or something.
She has the same problem as Professor Anita Shah had. Okay.
Yeah. Either you could just join the conference again, the link again, so that it will be okay.
No.
Because you're visible to us, but you're not audible.
You ask her to quit rejoin the.
Yes. I'm just quit the conference and join the link again. So the problems will be resolved. Ma'am, unmute. Yes.
she has
Hello.
done it. Okay, fine.
Yeah. You're audible.
Okay. Okay, so I just told what is a dominating set, and then the domination problem is to find a minimum cardinality dominating set, because just finding a dominating set is a trivial problem, because if you take just all the vertices of the graph, they form a dominating set. So the problem was introduced around 1860s by chess players. They wanted to know what is the minimum number of queens that can be placed on a square board, so that every square either contains a queen or can be attacked by a queen. But the mathematical study of the problem began around 1960s when Birch and Ore, actually they independently wrote book on graph theory where they mentioned the term domination. And after that, in 1998, these two books got published on domination, which has a lot of literature. And recently, these two books also got published. So these published very recently in 2020. And they have a lot of literature about domination. So here, as I'm going to talk about pair domination, so you may also refer this book, Topic in Domination and Graph, to know more literature about pair domination. It has a chapter which presents a lot of detail about the pair domination problem. So pair domination parameter was introduced in 1998 by Hennes and Slater, and it is very much studied parameter. So let me explain what is pair dominating set. For a graph, a subset of vertex at D is called a pair dominating set. So in the graph, there should not be any isolated vertex. So you may assume that always I will be talking about connected graphs with no isolated vertices. So if we have a subset D, subset of the vertex set, so that should be dominating set, and graph induced on D contains a perfect matching. Okay, so any dominating set D such that graph induced on D has a perfect matching is called a pair dominating set. And again, the problem is to find a minimum cardinality pair dominating set. And this minimum cardinality is called the pair domination number. So for dominating set, you know what is a motivation. Like basically we want to locate the facilities at minimum number of locations. Facilities can be anything. So like if you consider that you want to allocate guards or police officers at some location so that all the locations are covered using those guards or police officers, then a pair domination introduces the concept of backup. Like each vertex or each guard should also have a backup guard. So in case if something happens, that another guard can take care of his duties. So here each guard should have a backup guard. That concept is introduced in the pair domination. So that's why we said graph induced on D has a perfect matching. So each vertex in D has a pair. So in this graph, you can see that if you take these green colored vertices, they form a pair dominating set because they have a pair. And if you just look for dominating set, that even 3 vertices may form a dominating set. But in pair dominating set, you need 4 vertices. So this pair domination number is of course more than domination number because every pair dominating set is also a dominating set. And if you have a dominating set, which is not a pair dominating set, but I mean you are not able to find the perfect matching in that graph induced on D, then corresponding to each vertex, you see if it don't have pair, you can add a pair. Okay, so in this way, if you are having k vertices in the dominating set, by adding maximum k more vertices, you may get a pair dominating set. So pair domination number is at most 2 times domination number. Okay, so it lies between domination number and
Yeah, you're inaudible again. Hello, Aarti ma'am?
yeah, I think
Yeah, you're audible.
maybe I can switch off the camera and then I can speak. Maybe there is some
that
network
will
problem.
be better.
Yeah, so it is recently proved that it is NP hard to decide whether pair domination number is same as 2 times domination number. Okay, so when pair domination number will be same as 2 times domination number. Basically, like you have a dominating set, but no vertex is getting paired. So you need to take, if you are having k vertices in the dominating set, you need to take k more vertices to pair it up. So basically, you can say that every dominating set, whatever dominating minimum cardinality dominating set you are taking, that is basically an independent set. That time for every vertex you will have to add a new pair. Okay, so if every dominating set is independent set, that time pair domination number will be 2 times domination number. So there is no polynomial time characterization to check whether for a given graph pair domination number is same as 2 times domination number. And in this paper, they have also given the conjecture that it should be NP hard. According to them, it should be NP hard to decide whether pair domination number is same as a domination number for a given graph. but it is still open. So one can try whether can we check for a given graph whether pair domination number is same as domination number in polynomial time. Further, these are some bounds on the pair domination number for a graph. So if G is a connected graph of order n and minimum degree is at least 3, then pair domination number is 4n by 7. This is conjectured. Other than Peterson graph, for every graph, it should be less than or equal to 4n by 7. This is conjectured by Gordon and Henning in 2009. And then further, Lu et al. Have proved that this conjecture is true when minimum degree is at least 9. Further, they proved that this conjecture is true for R regular graph, where R is at least 4. And for connected clog-free graph of order n with minimum degree greater than or equal to 3, this conjecture is true. Okay, so for these graph classes, this conjecture is true, but in general, this conjecture is still open. And these are further bounds proved. So sorry, I missed a slide here. So this is already proved that pair domination number is less than or equal to 2n by 3. And further, when a graph is having at least 10 vertices, it was improved to this bound, 2n minus 1 by 3. And if G is a cubic graph of order n, then pair domination number is less than or equal to 3n by 5. And for clog-free graph, it is further improved. So these combinatorial results are known for pair domination. And since the problem is NP complete in general, most of the optimization problems are in general hard. So people either look for approximation algorithm for the problem, or they look for spatial graph classes where the problem is polynomial time solvable, or another recent thing is people look for parameterized algorithm for that problem. They see whether the problem is W2 hard. If it is not W2 hard, then they look for parameterized algorithm, polynomial kernel things. So for pair domination, there is an approximation algorithm with approximation ratio ln2 delta plus 1, where delta is the maximum degree. And this is a very simple greedy approximation algorithm. So if time permits, I will just give a quick idea behind this approximation algorithm. And it is very simple, a greedy approximation algorithm that one can think. But the analysis part is little tricky, like when you try to prove that this is the approximation ratio. But this is the best approximation algorithm, and it is also proved that further you cannot get any better approximation algorithm. So like we have an approximation factor ln2 delta plus 1, and it is known that it cannot be approximated with a sublogarithmic factor. Again, like when in the graph when maximum degree is 3, then the problem is APX complete. So when the graph is having maximum degree 2, you may observe that the problem is very simple. But even for graphs with maximum degree 3, the approximation also becomes hard. So regarding the spatial graph classes where the problem is studied, so these are the graph classes mainly where the problem is studied. Here I haven't put the references. So at the end, I have put all the references so you can find all these results in the references. And so here I have shown a line. Below this line for all these graph classes, the problem is polynomial time solvable. And for all the graph classes above this line, problem is NP hard. So, and for few graph classes, I have put up this question mark like circle graph, K-Polygon graph, dual equidal graph. So for these graph classes, the status of the problem is still unknown. And for planar graph and AT-free graph also, the status was not known. But in our recent work, we proved that the problem remains NP hard for planar graph. And we proposed exact polynomial time algorithm for AT-free graph, but the complexity of our algorithm is pretty high. It is n to the power 8.5, where n denotes the number of vertices in the graph. So we have also given a very simple linear time 2 approximation algorithm for the problem. So those results I am going to discuss in brief. Okay, so the status of the problem for planar graph was open, and it was also mentioned in these two papers. So this was a recent paper, but it also mentions that finding the complexity stages of the problem for planar graph is open. So we have resolved these answers to these questions. So let me first present the idea behind exact algorithm for AT-free graphs. So first I explain what is an AT. So if you have a graph, then a set of 3 vertices. So these 3 vertices should be independent vertices. There should not be edge between any pair of vertices. So a set of 3 vertices, 3 independent vertices is called AT. If you consider any 2 vertices, then there should be a path so which avoids the close neighborhood of the third vertex. So there should be a path between 2 vertices so that if you consider the third vertex, then no vertex from the close neighborhood of the third vertex should belong in that path. Okay, so there exists a path between them such that this path does not contain any vertex from the close neighborhood of the third. So for example, if you see this cycle, 6 cycles, so if you take these 3 vertices, they are forming an AT. These 3 red vertices are forming an AT because if you consider a path between any 2 red vertices, then there is a path which avoids the close neighborhood of third vertex. Okay, so if you consider these 2 red vertices, we have a path, and close neighborhood of this vertex is not present in this path. Okay, so these 3 vertices are forming an AT. So a graph is called AT-free if it does not contain any AT asteroidal triple. And for AT-free graph, we have a property that if a graph is AT-free, it has a dominating pair. So that we have used in our algorithm. So let me explain what is a dominating pair. A pair of vertices is called a dominating pair. If we take any path between these pair of vertices, then the vertices of this path form a dominating set. Okay, so we have a pair x comma y. If we take any path between x and y, then the vertices of this path form a dominating set. So since vertices of any path form a dominating set, we can take a shortest path between x and y. So that is called dominating shortest path. Okay, so we have a dominating pair xy, and if we take the shortest path between x and y, that is called a dominating shortest path. So every AT-free graph admits a dominating shortest path. So in this graph, you can see that V1, V3 is a dominating pair because if you consider any path between V1 to V3 and take all the vertices in the path, they form a dominating set. Okay, and if you see the shortest path between V1 to V3, that is V1, V2, V3, this is a dominating shortest path. So a dominating pair exists in every AT-free graph. It was proved by Cornell et al. In 1997, and this can also be computed in linear time. Then we have basically proved this theorem, lower one, with the help of the theorem given by Clocks et al. In 1995. So if we have a dominating pair xy and we make a BFS tree rooted at the vertex x. Okay, so from the vertex x, we have made a BFS tree. And in this tree, the labels are L0, L1, L2, and so on. So if we have a path from x to y where the vertices are x0, x1, x2 up to so on, this is the shortest path from x to y, then these vertices will appear in the corresponding labels, like x0 is in L0, x1 is in L1, x2 is in L2, and so on. And here we have property that if we consider any vertex in the label I, so of course that should be adjacent to one of the vertex in this path because this path is a dominating shortest path. So if we take any other vertex, that must be adjacent to one of the vertices in the path. But here we have the property that if we consider any vertex W in ith label, it must be adjacent to either xi minus 1 or xi. Because otherwise it can also be adjacent to xi plus 1. But here I'm saying it must be adjacent to either xi minus 1 or xi. Okay, so next, using this result, we have mainly proved this theorem. And this theorem says that if xy is a dominating pair, we have made the BFS tree rooted at x. Then if we consider any j plus 1 consecutive labels, so I to I plus j, if we consider any j plus 1 consecutive labels, then there exists a minimum cardinality pair dominating set, which contains at most j plus 4 vertices from these j plus 1 consecutive labels. So we can say from j consecutive labels, minimum pair dominating set contains at most j plus 3 vertices. Okay, so from this we get, if we consider 3 consecutive labels, we will get at most 6 vertices. There exists a minimum pair dominating set so that it contains maximum 6 vertices from 3 consecutive labels. Okay, so now we main idea comes from this theorem only. Now our algorithm is just brute force algorithm. Okay, so here we have seen that if we consider any 3 consecutive labels, then from those labels, maximum 6 vertices should be presented, minimum pair dominating set. Down we make a BFS tree, and basically from the root, first we consider L0, L1, L2 label. And from these 3 labels, we try to pick set of cardinality 6, all the sets of cardinality 6. So cardinality maximum 6. Okay, so cardinality less than equal to 6. And then we see, so in the starting, like we have taken vertices from L0, L1, L2. So we take a subset of labels from L0 to L2, and they should dominate L0 and L1. And they should also pair all the vertices which are present in L0 and L1. Okay, so basically what we will do, we will maintain a triple of this kind, x dash, psi j of x dash. X dash dominates all the vertices up to ith level, and x stores the information of vertices present in x dash from only 2 labels. So basically we have to see the information from 3 labels. So that's why we maintain from 2 labels. And next time when we further add one more label, then we make sure that from these 3 consecutive labels, we are not adding more than 6 vertices. So in this way, we are just taking all the possibilities so that we are not taking more than 6 vertices from 3 consecutive labels. So when we are taking the sets in this way, so basically when we consider, even if we consider all the sets of cardinality 6, then that will be NC6, roughly order of n to the power 6. And for each set, we also need to check whether they form a pair dominating set or not. So for that, we need to check whether there is a perfect matching exist or not. So that we will check in, that we can check in n to the power 2.5 time. So overall complexity will be n to the power 8.5. Okay. So here what we have done is store all the possible sets. Basically here we will have collection of sets. We store all the possible sets such that x dash dominates all the vertices till ith level. Okay, so this is the work done in ith iteration. Store all the possible sets such that x dash dominates all the vertices till ith level. Ensure that all the vertices in up to ith level are paired, because right now basically we are taking vertices from I plus 1th level. Later we will not take more vertices from I plus 1th level. So all the vertices up to ith level must be paired. Since they cannot be paired with I plus 2th level, right? So in this way, we just store all the sets, and at the end, we will output the set with minimum cardinality. So based on this idea, our time complexity is n to the power 8.5, which is pretty high. And if we apply our approach in bit systematic manner, it can be little bit improved. But I think there cannot be much improvement using this technique. So one can come up with some other technique by which the complexity can be reduced. But since the complexity is very high, we have also proposed a linear time approximation algorithm that is very simple algorithm. So let's see what is the approximation algorithm. So if it is an 80-free graph, we know that there exists a dominating pair. Let P be a dominating shortest path. Now consider all the vertices of this path. Suppose the number of vertices in this path are t. Okay, so here one important thing you have to note, and all the idea of approximation algorithm is based on this idea only. So here we notice that any two adjacent vertices in G dominates at most the 4 vertices of P4 in P. Okay, so if you consider 2 vertices from the path, then of course, so we are considering adjacent vertices. Because in pair dominating set, for every vertex, you also need to take its pair. So when you are taking 2 vertices, consecutive vertices from the path, they can of course dominate at most 4 vertices of the path. But if you are taking 2 vertices from outside, then also they can dominate maximum 4 vertices of the path, because like this, if they are dominating 5 vertices, suppose A, B are the vertices and they are dominating x1, x2, x3, x4, x5, that time we will get a shorter path from x to y. So we can move from x to x1, x1 to A to B, B to x5, and so on. So in this way, we will get a shorter path. So that's why any two adjacent vertices can dominate at most 4 vertices of the path. Right. So total number of vertices in the path are t. So to dominate all the vertices of this path only, we need at least 2 times CL of t by 4 vertices, right? So our pair domination number must be greater than equal to this thing. So first thing is we observe this bound, that pair domination number is at least this much, 2 times t by 4. Now, how we construct a pair dominating set. So as a pair dominating set, we simply see the number of vertices in this path, dominating shortest path. If they are even, we just output that as a pair dominating set. If the number of vertices are odd, we just add one more vertex. Okay, because we should have even number of vertices. So this path is already a dominating path. If it is having even number of vertices, then it is fine. If it is odd, we add one more vertex. So in this way, we have a dominating set. And as we said that we have this inequality, using this, we can claim that cardinality of our dominating set is at most 2 times pair domination number. So it is giving 2 approximation algorithm. Okay, so this is a simple linear time algorithm because we can compute dominating pair as well as dominating shortest path in linear time. And its approximation ratio is 2, which is also pretty well. Okay, so next I will move to another result, that is NP completeness for planar graph. So before that, if you have any questions, you may please ask.
Question can be asked in the end also, Pran.
Okay, ma'am.
We leave the question out in the end.
Okay, ma'am. So I have 15 minutes, ma'am.
Yes, more than 50 because there was some trouble.
Okay, okay, ma'am.
You take another 20 minutes, okay?
Okay, ma'am.
Because there were some troubles, I'm giving you a little more time, okay?
Okay, so to prove NP completeness for planar graph, we have made a reduction from vertex cover problem. So what is a vertex cover problem? Given a graph, a subset of vertex sets, say VC, is called a vertex cover if every edge has at least one endpoint in VC. And the vertex cover problem is to find a minimum cardinality vertex cover. Suppose beta G denotes the cardinality of minimum vertex cover of G. Okay, so we have made reduction from vertex cover problem. So if this problem is already known to be NP complete for cubic planar graphs. So planar graph where degree of each vertex is 3. So now what is the construction? Given a cubic planar graph, we construct another graph that will be instance of our pair domination problem. So here, corresponding to each vertex in the graph G, we have taken a gadget here. Okay, so this gadget is corresponding to each vertex in the graph G. Now what to do for edges? Like from one particular vertex, there can be 3 edges. Okay, right, like we say EJ, EK, EL. These are the 3 edges incident on a particular vertex VI. So if this vertex, this gadget represents vertex VI, so you can make EJ incident on VI1 EK incident on VI3, EL incident on VI2. Okay, so whenever there are 3 edges incident on a vertex V in the graph G, we make 1 edge incident on VI1, 1 edge incident on VI2, and 1 edge incident on VI3. Okay, so this is the construction of the graph. Now we prove that pair domination number of the constructed graph will be 4n plus 2 beta g, where beta g is the vertex cover number and n is the number of vertices in the graph G. So how this proof works, I will give a simple idea from one side. So suppose we have a vertex cover VC. VC is a vertex cover. Then how we take edges in the pair dominating set. So if a vertex Vi is present in the vertex cover, that time we want to take Vi1, Vi2 and Vi3 in the pair dominating set. So actually vertex cover is also a dominating set. So that concept we are using here. So if a vertex is present in the vertex cover, that time we want to take Vi1, Vi2 and Vi3. So if we want to take this one, we also need to take their pairs. So we will have to take Vi1 by I1, Vi2 by I4 and Vi3 and Zi2. So in this way, we will take these 6 vertices from the gadget and you can see that all these 6 vertices are dominating all the vertices of this gadget. So basically, if a vertex is present in the vertex cover, we will take 6 vertices from the gadget. And if a vertex Vi is not present in the vertex cover, then we will take only these 4 vertices in the gadget. So these 4 vertices dominates all the vertices other than Vi1, Vi2 and Vi3. Okay, so basically this Vi1, Vi2, Vi3, whenever we have introduced them, they are dominated using vertex cover, the vertices corresponding to vertex cover only, right? So Vi1, Vi2, Vi3 are representation for representing vertices for the vertex Vi in graph G. Okay, so from each gadget, we are either taking 4 vertices or 6 vertices. So if beta G is the vertex cover number, so if we have taken a vertex in the vertex cover, from that gadget, we are taking 6 vertices. If we have not taken that particular vertex in the gadget, then we are taking 4 vertices. Okay, so in this way, the cardinality of our pair dominating set will be this, which is 4n plus 2 beta g. Okay, so if we have a vertex cover whose cardinality is beta g, we get a pair dominating set whose cardinality is at most 4n plus 2 beta g. Okay, and similarly, we can also prove the converse. In the converse, we will have that like from again when we have a pair dominating set whose cardinality is 4n plus 2 beta g. So it is sure that in pair dominating set you will have to take at least 4 vertices from the gadget, and if you take more than 4, then you will have to take 6. So whenever you are taking 6 vertices in the gadget, then from that particular gadget, you corresponding vertex Vi you take in the vertex cover, and that set will form a vertex cover. So this was the NP completeness proof for planar graph. So I wanted to give some idea for approximation algorithm. So I will just describe in one line. So as I said, it is very simple greedy algorithm. So what is the algorithm? You have to compute a pair dominating set. So all the vertices of the graph should be dominated, and for each vertex there should be a backup. So we pick a pair of vertices so that there exists an edge between them. We pick 2 adjacent vertices, and they should dominate maximum number of undominated vertex. So every time, basically, we just in every iteration, we pick 2 vertices which are adjacent and they dominate maximum number of undominated vertex. Okay, so we just do this in all the iteration. This is the greedy procedure, and then we prove that this achieves an approximation ratio of ln 2 delta plus 1. I will not describe the analysis. I would just like to describe another domination parameter, which is the recent one. So pair domination is very well studied. So as I have described, there is there is few scope like K polygon graphs, or for circle graph, the status of the problem is still not known. But most of the things are already studied for pair domination. But semi-pair domination is a recent variation of domination, so still there is a lot of scope for this problem. So it was introduced by Hannes and Henning in 2018. So a dominating set is called a semi-pair dominating set if for every vertex in this set you have a pair which is at either distance 1 or distance 2. So in pair domination, for every vertex, you should have a pair at distance 1. Here you are relaxing that little bit. You are saying that for every vertex, you have a pair that can be either at distance 1 or at distance 2. So minimum cardinality of a semi-pair dominating set is called semi-pair domination number, and it is denoted by gamma pi2g. So for this graph, you can see that these are the basically same graph, but for this, the pair domination number is 4, but semi-pair domination number is 2. So here for this red vertex, the backup is this red vertex, and this is at distance 2. But here we should have a backup at distance 1 in pair domination. So we need to take 4 vertices. So semi-pair domination number is basically sandwiched between domination number and pair domination number. So again, it is of independent interest, but it is of interest because it is sandwiched between two important domination parameters. And we have analyzed that there are some graph classes where one problem is polynomial time solvable and another is hard, and vice versa. So in that way, it may also be helpful in giving the bounds on these parameters because the complexity status of these parameters are not same. So these are some combinatorial results studied for the problem. So till now, there are only few papers published on these parameters. So these were the combinatorial results. And further, we have proved some algorithmic results. So we proved that it is NP complete for bipartite graph, coordinate graph, and split graph. And we can compute semi-pair dominating set, minimum cardinality semi-pair dominating set for trees, block graphs, and interval graphs. But it is not studied for any other graph class. Okay, so till now only this is the status for graph classes. So one can further study for many graph classes like strongly caudal, dually caudal, doubly caudal, undirected path graphs. So there are in bipartite hierarchy one can study like for convex bipartite graph. So for convex bipartite graph or caudal bipartite graph, pair domination is polynomial time solvable, but the status of semi-pair domination is open. So one can work on those things. And in approximation aspect, again, we have gotten 1 plus ln2 delta plus 2 approximation algorithm. And we cannot do further much better. This also we have proved. And we have shown that it is apex complete for graphs with maximum degree 3. And if we consider especially bipartite graph, then for graphs with maximum degree 4, it is apex complete. So based on these results, we have basically published 2 papers. One is in discrete mathematics and theoretical computer science, and another is in theory of computing system. This is joint work with Professor Henning and my PhD student Vikas Tripathi. So he is also working on domination problems. So this was all about my presentation. So here basically I have discussed about pair domination problem, and I also talked about semi-pair domination because there may be more scope to work on this new parameter because pair domination is already very well studied. So so one thing is like we have proved that pair domination is NP complete for planar graph. So one can try whether there is parameterized algorithm for pair domination in planar graph, because for some of the domination parameters, we already have parameterized algorithm for planar graph. So here also we may try the same thing. Another thing is we can try better algorithm in case of AT-free graphs. As we said, our time complexity is high. And status of the pair domination is still open in circle graphs, dually caudal graph, and pair polygon graph. So these are the research directions in a pair domination problem. But for semi-pair domination, as you have seen, there are many open questions one can work on. These are some of the references. So these are all the papers on pair domination. So you can see like for spatial graph classes like a strongly caudal graph, block and interval graph, generalized claw-free graph. And more literature about domination, a pair domination problem can be seen in that book, Two Optics and Domination, that I have said. So it has very good literature survey on the problem. Okay, so it is all about my presentation. Thank you.
So I ask the participants, the listeners, to ask some questions or their thoughts or their queries from Aarti Pandey. So I am not finding anybody asking questions. Anyway, Aarti, I have some queries. Okay.
Yes, ma'am.
That is, you gave in the last that gamma g less than or equal to gamma PR2 less than or equal to gamma PR. Okay, that inequality you gave. Do you have graphs for which they are equal? Equality is attained.
Pair domination number is same as semi-pair domination number.
Yeah, and same as domination number. Do you have graph here? It is that equality.
If we take a complete graph, then pair domination number will be same as semi-pair domination number, but domination number will be less.
Domination number will be less. But I want where it can be equal. Do you have any graph?
Yes, I think we can make a graph in this way, like we take an edge, we have an edge UV and make some vertices adjacent to U, also make some vertices adjacent to V. Maybe we make 10 vertices adjacent to U and 10 vertices adjacent to V. So in this way, like we will have to take UV in the dominating set. That is a pair dominating set, and that is also a semi-pair dominating set.
Is it a dominating set also?
Yes, ma'am. So I said take U and V, take an edge between them.
Okay. Okay.
And then make 10 vertices adjacent to U and 10 vertices adjacent to V.
Means it's a it is your bi-star.
Yeah, it is bi-star. Yeah.
Bi-star. Now, similarly, if I take a cycle of length 4, for which a domination number is equal to pair domination number, is it?
Cycle.
C4.
Yes, ma'am. Yeah.
And
even semi-pair domination number is also same. Yes, ma'am. Yeah.
And if I take a path on 4 vertices, there also.
Yeah, so there also it will be true. Yes.
Okay. But for bi-stars, it will be really easy to find out because we want a pairing. Na? Okay. Okay. Thank you very much for your wonderful talk. And I hope the students will get interest in this one, pair domination, and what other you have introduced, semi-pair domination. But it's interesting, this one. I'm getting interest in pair domination number. Thank you, Aarti. Thank you.
So thank you so much, all the organizers again for giving me this chance.
Thank you, Mukti ma'am, for chairing this wonderful session. And thank you, Aarti ma'am, for the session itself. So now I'll just request everybody to switch on the camera so that we can have a group photo. And then we'll move on to the parallel sessions, the paper presentation sessions. Yeah. Okay, so now all the participants can join any one of the links for the parallel session using the links were provided before. And the session will start immediately just after this. And I also request all the paper presenters to be ready for their turn. We'll meet in the paper presentation session now.
Thank you very much, Aditi.
Thank you. Thank you. Thank you, ma'am. Thank you.
Thank you, madam. Thank you, madam.
Thank you, everyone.
I have to go to other this one, so I have to rejoin, okay?
Yes, ma'am. Yes, ma'am. We'll have to rejoin.
Okay.